Hello and welcome to today's class. So we are going to look at how differentiation is used in the study of kinematics. All right. So basically, kinematics is study of motion. So when we talk of kinematics, we are talking of displacement. Displacement. Sorry. So displacement basically is a polynomial that usually describes how distance changes. All right, how distance changes uh, in different times when there is motion in an object. All right. So usually it is given as a function of time. All right, as a function of time because distance is measured over time. All right. Then when displacement changes, when there is rate of change in displacement, usually we have velocity. All right. So velocity is this is the rate of change of displacement. Okay, the rate of change of displacement over a given period of time. Of course, yeah, over a given period of time. So most of you will relate to velocity also as speed, except that when we are talking of velocity, then we are speaking of uh, change of displacement uh, at a particular direction. Okay, when you talk of the velocity and like speed, we are talking of speed at a given, at a given direction. Okay, not just random directions. Okay, so velocity and speed basically at the same time, the same thing. But usually velocity is as a result of displacement. All right, it is usually as a result of displacement. And so when velocity or speed also varies of an object during motion, then we talk of acceleration. Okay, we talk of acceleration. We talk of acceleration. Maybe if I give you a scenario here, all right. So let's say that we are having point A and point B, and we have an object that is moving from point A to point B. All right. Okay, so the distance that it covers from A to B will be described by a function, called displacement, and it is usually in respect to time. Let me give you an example of how a displacement function will look like. Then it becomes easy to relate. So an example of a function that is basically describing displacement would be the function s, all right, 2t cubed, all right. So where t is a variable that describes time, plus 4t squared, all right, minus 8t plus 3. So this here is an example. This is an example of a function that is describing displacement, which is basically a change of distance over a given period of time. All right, over different periods of time. Maybe in 1 second. Okay, what will be the distance covered in 1 second, or what should be the distance maybe we expect to have been covered in 3 seconds, and all that. So that is what displacement is. However, when we talk of an object moving from point A to B, we're talking of when you're talking of how fast that distance it's covered, then we talk of velocity. So velocity comes in when we're talking of how fast that moving object covers the distance from A to B. All right. So the function that just describes the movement from A to B is displacement. All right, which we have here, and usually it is it is written with respect to time, as that is how we then be able to measure velocity as well. So velocity then talks of how fast that distance is covered. And now when we talk of acceleration, we are talking of the change of velocity. All right, you see, as much as the motion of an object moving from A to B is fast, it can move faster. All right, so it can begin, let's say, at a velocity of 33 kilometer per hour. All right, and then that is in the first second. Okay, in the first second. Then you notice that when it gets to the second, it's able to change its velocity, let's say, to 40 kilometers per hour. So this change, okay, sorry, per hour. So this change, this is, let's say, in the third second, right? So this change of velocity, all right, is what we refer to as acceleration. So basically, when we talk of kinematics, then we are talking of the study of objects under motion, and we are looking at the equation that describes displacement, velocity, and acceleration. Let me say this before I do an example. That when you have displacement, all right, when you have displacement and you differentiate it, usually what you get is a function that is describing the velocity of the moving object. All right, whenever you have a function describing displacement and you differentiate it, then you end up having a function that is describing velocity. All right, then when you go ahead and do a second differentiation, all right, when you derive it for the second time, which is basically when you differentiate it for the second time, then what you end up with is a function describing acceleration, describing acceleration. So that is going to be the basis of this class. We are going to solve problems and see how we can use displacement function to find velocity at different times and acceleration at different times. Let us handle our first example. Awesome. So we are going to first handle this example that mainly looks at how to solve problems related to velocity. So we having that the displacement s meters, all right, covered by a moving particle after time t, that is in t seconds, is given by. So this is the displacement of a moving particle, all right. A moving particle covered after time t, which is a variable. Of course, t is in seconds. All right, is given by s equals to t raised to 3 or t cubed plus 4t squared, right, minus 8t plus 3. All right, so we are having this here as the displacement, which is basically a function that is describing our distance from point A to B, all right, changes in at different times. All right, so we are told to find the velocity, that is the speed, at t2, at the second, and at the third second. All right, that is our first part of the question. And then our second part of the question is that we are supposed to find the instant at which the particle is at rest. So that is when, at what time is the particle not moving completely. So let us solve this. So remember, for us to talk of velocity, for us to find velocity, we have to first differentiate. What? Displacement. So when we differentiate our function s here, we are going to get our function that is describing the velocity of this moving particle. So we are going to, to solve, velocity at time 2 and time 3, we're going to first of all find the function that actually describes velocity of this moving particle, all right, with the function given below. So we're going to find the derivative of s with respect to t, and so that will be 2 times 3, all right, that will give us 6, all right, t raised to 3, that is 3 minus 1, and that will be t squared. So it will be c t squared, all right, plus 2 times 4, all right, 2 times 4, and that will be 8. All right, t, that is 2, 2 minus 1, that is just 8t. All right, then here we are going to have 1 times negative 8, and that will be negative 8. 1 minus 1, of course, will give us 0. Any number raised to 0, that is t raised to 0, will give us 1. So 1 times 8 will give us 8. And anytime we find the derivative of a constant, we always get 0. So basically, 6t squared plus 8t minus 8 is going to be our velocity function. All right, so this is our velocity function. So for us to find the velocity, all right, of this moving particle, all right. For us to find the velocity of this moving particle at t raised to 2, will basically come and write this function with t being equal to 2, all right. So velocity at t equals to 2 will be 6 into, where we have t we put 2, 6 into 2 squared plus 8 into 2 minus 8. Of course, so this is going to give us velocity in meters per second. Remember, the displacement was in meter, all right, and meters, and it was with respect to time t seconds, all right. So in your calculator, when you do this math here, you'll get that the velocity is actually equal to, yes, you'll find that the velocity is actually equal to 32 meters per second. All right, that is at the second, second, all right. At t equals to 2, then you'll find that the velocity is actually equals to 32 meters per second. And now, for us to find the velocity at t equals to 3, all right, we'll basically do the same thing we've done for 2, but now instead of having t equals to 2, we'll have t being equal to 3. So velocity at t equals to 3, all right, velocity at t equals to 3 basically will give us, let me have some space here, will give us 6 into, so where we have t we put 3, all right, it will give us 6 into 3 squared plus 8 into 3 minus 8. And so when you put that in your calculator, you get, yes, when you do that in your calculator, you get that the velocity will change, and at t equals to 3 to 70 meters per second. So those are the two velocities at t equals to 2 and t equals to 3. So we first of all found the velocity function, then substituted from the velocity function the value for t. So we had t equals to 2 here, and that was giving us that at t equals to 2, velocity will be 32 meters per second, and that at velocity t equals to 3, we are getting that velocity will be 70 meters per second. So now let us solve the part B of this question, and that is, at what instant do we have the particle at rest? All right, so we have the particle at rest when it is not moving. We all know that, all right? So at what instant will the particle not be moving? It will be at rest when velocity is equal to 0. That means that it's not moving. There's no change of distance at all. So for us to solve this question, we'll basically equate our velocity function to 0, then solve the quadratic equation thereof. So for part B, we basically have 6t squared, all right, plus 8t minus 8 being equal to 0, all right. And so we can solve this using quadratic equation. You can solve it using factorization. You can solve it using quadratic formula, all right. You can solve it using completing square method, all right. It's up to you which method you want to use. All right, let us see if we can solve it using factorization. Okay, all right, so we notice that there's a common factor in 6, 8, 8, and 0 here. So we are going to divide all these terms by the common factor, which in this case happens to be 2, all right? So we're going to divide by 2, all the terms by 2. And so when you divide all the terms by 2, notice we are going to having 3 t squared plus 4t minus 4 equals to 0. Okay, equals to 0. All right, then we note that, of course, that is very correct. That is correct. We don't have any other common factor here. So what we are then going to do is we are going to find the product all right, the product we're solving using factorization. So the product in this instance will be gotten by multiplying a and c. So our a is 3, all right, and our c is -4, all right. So our product will be equal to 3 times -4, and that will give us -12. And so our sum basically will be the value of b, which is 4. All right, so what two numbers do we know of that when we multiply them will give us -12, and when we add them will give us 4? Two numbers that when we multiply will give us -12, and when we add them will give us 4. So notice that when you take -6 and +2, actually when you multiply -6 times 2, you'll get -12, and when you add -6 plus 2, you get not -6, but when you take 6 and -2, all right, 6 and -2, so 6 times -2 will give you 12, -12, and then when you take 6, okay, 6 plus -2 will give you 4. 6 plus -2 will give you 4. So basically, we're going to rewrite the whole equation using 6 and -2. All right, so we're going to have 3t squared, all right, plus 6t minus 2t. All right, so those are the two factors we chose, 6 and -2. Of course, when you add these two, gives you 4. All right, minus 4 equals to 0. All right, then when you pair those two there, you're going to get that 3 is a common factor, so it's going to be 3t squared. Yeah, 3t is actually the common factor, so it's going to be 3t squared divided by 3t, that is actually t, all right, plus 6t divided by 3t, which will give you 2. All right, and so in here, when you have the two pairs combined together, you're going to have that the common factor is -2. All right, so that when you take -2t divided by -2, you get t. All right, and 4 divided by -2 will basically give you positive 2, and that being equal to 0. So we will take one of those, and so when you take one of those, we are going to have 3t minus 2 and t plus 2 equals to 0, and t plus 2 equals to 0. And so basically we can find the value of t1 and t2 from this particular problem. All right, the value of t1 and t2 from this particular problem. Awesome. So just a continuation from where we left. So we are trying to solve the time when the object won't be moving. At what time will the object be at rest? So we have solved the factorized equation of our velocity function, and so we've reached here. So we want to determine the value of t. All right, so we always assume that it's either the left hand side bracket that will be equal to 0 or the right, so that when you take either, then it's always equal to 0. Remember, any number multiplied by 0 is 0. So we don't know which one is 0, whether this or this. So we'll assume that either of them may be 0, and so we'll equate each of them to 0. So for us to find t1, we are going to have 3t minus 2 equals to 0. All right, that is for t1. And so basically this will give us 3t being equal to 2. And so the value of t when you divide both sides by 3 will be 2 over 3. All right, 2 and a third seconds. All right, so this is going to be our value for t1. All right, that's going to be our value for t1. And so our value for t2, when you're trying to find t2, all right, we're going to equate the other bracket to 0. So that is going to be t plus 2 equals to 0. All right, so basically that's going to be 2 being equal to -2. All right, and you see it's -2 seconds. We know very well that we will never have time being measured in negative numbers. So basically, that means therefore that of the two values of t, that's t1 and t2, we won't pick t2. All right, we won't work with t2. Why? Because it's measuring time as a negative number. And so we are going to then state that the time when the object is at rest is actually at 2 1/3 second. All right, 2 1/3 second is the time when the particle is at rest. So we have emphatically determined that it's at 2 1/3 second that the particle will be at rest. And so that solves this particular problem on velocity. That's it for velocity. Let me handle. I'll post the next video, basically solving a problem on acceleration. So we see how we can also use differentiation to solve problems related to acceleration. Thank you, and see you in the next video.